So in this video, let's look at a naive divide and conquer algorithm to solve polynomial multiplication problem. The idea is we're going to take our long polynomial and we're going to break it into two parts, the upper half and the lower half. So a sub x is going to be d sub 1 of x times x of n over 2 plus d sub 0 of x, which is the bottom half. D sub 1 of x, since we've pulled out x sub n over 2 terms, its lowest term is actually just a sub n over 2. So we have two parallel subpolynomials, the high and the low. We do the same thing for b, so we break that into e sub 1 of x and e sub 0 of x. Again, where e sub 1 of x is the high terms, e sub 0 of x is the low terms. When we do our multiplication, then we just multiply together d1 x sub n over 2 plus d0 and e1 times x sub n over 2 plus e0. And that then yields four terms. D sub 1 e sub 1 times x sub n, d sub 1 e sub 0 plus d sub 0 e sub 1 times x sub n over 2 plus d sub 0 e sub 0. The key here is that we now just need to calculate d1 e1, d1 e0, d0 e1, and d0 e0. Those are all polynomials of degree n over 2. And so now we can go ahead and use our recursive solution to solve this problem. So that gives us a divide and conquer problem. Its runtime is t of n equals 4 t of n over 2. Why 4? 4 because we're breaking into 4 subproblems. Each of them takes time t of n over 2 because the problem has been broken in half. Plus then, in order to take the results and do our addition, that's going to take order n time. So some constant k times n. Let's look at an example. So we have n is 4, so we have degree 3 polynomials, and we're going to break up a of x into the top half, 4x plus 3, and the bottom half, 2x plus 1. Similarly, we're going to break up the top half of b of x cubed plus 2x squared just becomes x plus 2, and 3x plus 4 stays at 3x plus 4. Now we compute d1 e1, so multiplying together 4x plus 3 times x plus 2 gives us 4x squared plus 11x plus 6. Similarly, we calculate d1 e0, d0 e1, and d0 e0. Now we've done all four of those computations. B is just d1 e1, 4x squared plus 11x plus 6, times x to the fourth, plus the sum of d1 e0 and d0 e1 times x squared, plus finally d0 e0. If we sum this all together, we get 4x to the 6th plus 11x to the 5th plus 20x to the 4th plus 30x cubed plus 20x squared plus 11x plus 4, which is the correct solution. Now, how long does this take to run? We're going to look at that in a moment. Let's look at the actual code for it. So we're going to compute a resulting array from 0 to 2 to the n minus 2. So those are all the result coefficients. And our base case is that if n is of size 1, we're going to multiply together a at a sub l plus b at b sub l. Let's look at those parameters again. So a and b are our arrays of coefficients. N is the size of the problem. A sub l is the first coefficient that we're interested in, and b sub l is the coefficient in b that we're interested in. So we're going to be going from a sub l plus 1, a sub l plus 2, etc., n for n times. First thing we'll do is multiply together the d sub 1 and e sub 1. So basically what we're doing, the d sub 0 and e sub 0. So what we're doing is taking a and b, we're reducing the problem size by 2, and we're starting with those same coefficients. And we're going to assign those to the lower half of the elements in R. Then we're going to do something similar where we take the upper halves of each of a and b. So again, the problem size becomes n over 2, but now we're moving the low coefficient we're interested in from a sub l to a sub l plus n over 2, and b sub l to b sub l plus n over 2. And we're going to assign those to the high coefficients in our result. Then what we have to do is calculate d sub 0 e1 and d1 e0, and then sum those together. When we sum those together, we're going to assign those to the middle elements of the resulting array. And we'll then return that result. Now the question comes up, how long does it take? So we have an original problem of size n. We break it into 4 problems of size n over 2. So level 0, we have size n. Level 1, we have size n over 2. At level I, our problems are of size n over 2 to the I. And all the way down to the bottom of the tree is at log base 2 of n, and each of the problems are of size 1. How many problems do we have? At level 0, we have 1 problem. We have then 4 problems. If we go to the ith level, we have 4 to the I problems. And at the very bottom, then we have 4 to the log base 2 of n problems. How much work is there? Well, we just need to multiply together the number of problems times the amount of work. So we have kn here. And then we have 4 times, 4 because there are 4 problems, kn over 2. Because the problem size is n over 2, and the amount of work we're doing at each level is k times n over 2 per problem. So 4k n over 2 just equals k times 2n. At the ith level, 4 to the I problems. Each problem takes k times n over 2 to the I to deal with. We multiply together k 2 to the I times n. And at the very bottom, we have k amount of work. We have a problem size of 1 times 4 to the log base 2 of n. Well, 4 to the log base 2 of n is just n squared. So we have kn squared. Our total, as we sum up all the work, is going to be the summation from I equals 0 to log base 2 of n of 4 to the I, k times n over 2 to the I. And that just gets dominated by the very bottom term, which is theta, big theta of n squared. So that's what our runtime takes. This is kind of weird. We went through all this work to create a divide and conquer algorithm, and yet the runtime is the same runtime as it was with our naive original algorithm. We're going to see in the next video a way to redo our divide and conquer algorithm so we have less work to do at each level, and so we actually get a better final runtime.